So in our example, we say that, well, maybe we want to have an array. And it's an array of, to begin with, like 5 integers was one of the arrays. Then, or maybe more, I'll just make it more regular, I guess, looking. Or an array of characters. And there is a limitation, whatever these arrays contain. When we were able to hard code the size of our array, right? Before it was like 6 and 5. This was okay because the compiler knew precisely how big this stack frame has to be to accommodate those local blocks of integers or characters. It was a no-brainer. Just look at this. When we switch to a variable, although we don't even ask the user, but now we use a variable. So a variable is really significant impact on the array allocation, right? So it truly is a variable. We don't know what the size might be. And therefore, compiler rejects this. And if we try to compile it, the compiler is not going to allow this to happen. Instead, it says, expected constant expression right here. Expected a constant expression. Like 6 plus 5. That's a constant expression, right? So there's no variables involved. Okay. But we want to use a variable. So this limitation of the stack frame allocation is the reason why this is not permitted. Right? In other programming languages, it's okay to do something like that. But in C++, arrays really are a low form, very rudimentary facilities to store data, just blocks of memory. That's all they are. And even inside the array, we store an address, which is really kind of lowest level of data that you can possibly get to. Right? Which may look somewhat intelligent with square brackets when we try to access individual elements, but hey, under the hood, it's a very, very primitive data structure. Okay, and serious limitation on this. So, if we want to use a variable, an array needs to be allocated dynamically. When the array is allocated dynamically, the stack, and I will just kind of draw a punctured line to say that, once in a while we call print function, and this stack frame is also constructed. So this stack area is no longer used. Instead, let's perhaps redraw something here while keeping this in view. So our program loads in memory, and it's constructed out of different memory segments. Okay, so this is our program taking space and memory. There is code, right? Code. It's typically named segment text, but that's where our executable code is sitting. Then there is, not necessarily in this sequence, but in general, different segments. Then we have something called a constant segment. For example, all strings like this, which are officially constant objects. They're not modifiable. There is no way that we're not allowed to modify this memory, right? You can create an array to do something like that. But if you just use a string literal and you know it's sitting in memory, you cannot go at that memory and change it. So all these strings will be sitting in this constant memory segment, and the CPU knows that it's protected and you cannot change any data there. Then there is also an area called global. Any global variables that's supposed to be shared by different functions, they will be sitting in this global segment. this is zoomed in stack, right? So the stack where all the local variables are allocated, and remember, stack is manipulated as the functions are invoked. Each call to a function results in the creation of a stack frame. So the stack may grow in a direction of lower addresses, and so it can dynamically grow, and then as functions are being called, and then it goes right back to the lower level when functions return. So there's definitely a stack pointer, which is like a stack register inside the CPU, ESP, for that matter, on Win32 platform, that basically watches the current stack position. Okay, and this area is called free store. Free store. Free store is managed memory by the memory which is managed by the new and delete operators. Okay, so now I want to allocate my array of characters by specifying how many. So my choice really now becomes to say, well, I want an array, but I really kind of have to switch to use a pointer. And the syntax becomes this. I want this many. And initializer is no longer available, at least in the previous version of C++ standard. And I'm saying, give me this many characters, but I must say new. Okay, so initializer is no longer available. Just scratch that idea, right? But what's going to happen is that this array of characters dynamically will be allocated. Let me kind of scroll this so we can see both of these things. So this array of characters is now dynamically, and we tell how many characters we want, right? We could have asked the user. They're all will be allocated here on the free store. That's where this brand new array will be allocated for us. And more so, on this free store, in front of this array, there will be a number of elements remembered. For what reason? For the reason that we, at some point, we may want to say, we no longer want to allocate this array of characters because it's taking too much space. We may need this memory space for something else. And in that case, we will say delete. Empty set of brackets, charr, if that was the name of our array. If we do something like this, then what's happening is that the free store management, which is managed by new and delete, the result of compiling new and delete is this free store management that is taking place. What's going to happen here is that the number of characters, like 6, is stored in memory here. When we say delete with this set of empty square brackets, we're telling this free store manager to go ahead, take a look at how many characters being specified there, go at this location. Obviously new returns a pointer, right? charr is now a pointer to a character, to the first character in this block of this many characters in memory. But anyhow, delete now will be able to kind of find this in memory, right? So this is what delete does. It finds this block of characters in memory. Then it kind of knows that because we're asking the compiler to delete an array in memory, it will retrieve the number of elements stored, so how many elements are present, and basically will mark this memory as free. And so doing this 2 times in a row will be actually a very significant violation and may result in unpredictable behavior. So it's dangerous. It's quite dangerous. So new and delete must match. They must match. So which brings us to maybe some ways of managing it better